Okay, we're going to start the seminar now. So if you haven't already, please take the photo of the QR scan and fill out the form. So okay. So thank you all for coming here. Today, myself, Streyas, and Miles will be hosting this seminar. We will be mainly focusing on the second half of the course, so starting with binary search trees all the way up until OOP. And yeah, we can start with the seminar now. So we'll first start with memory models. So the first question will be, with this block of code, I want you all to fill out this memory model. Can you guys see the blackboard? Yeah, okay. So from this code, fill out the memory model and answer the corresponding questions. So yeah, I'll give you guys some time to solve this, and then I'll take it up. Yeah.
So for the line x, the zeroth element of x, does that mean that map that dynamically allocated starts at 1500 and that the line below is also there 1500 or?
So this dynamically allocates 3 boxes of memory, and X0 stores the memory address of the initial box. So anything that's in the main function would use lockers from 4.1 to 10.14. Yeah. Yes, it starts at 401. 401. Yes. Both the main initializer starting from 401 and the array X. Oh. Yeah. Okay.
A lot of people have been asking, this is going to be recorded. We still have to get permission from Marcelo in terms of the slides, but at least the recording itself should be posted by tomorrow latest. So, yeah.
Okay, I'll start taking up the question now. So, any time I ask a question and anyone who gives a reasonable answer, you'll throw out chocolate. So, yeah. Okay. Okay, so the first thing that we should note in this body of code here is that our function is void. It's not a int main, it's a void main, meaning that we don't have a return value for a function. So you'll start off with the second line, where it declares a pointer array called x with 3 elements in it. So it says for us to declare it starting at box 401. So and note this is int pointer of 3. So our second line states that x0 is where we dynamically allocate with malloc 3 integer size memory addresses. So it says it's allocated a locker 1500. So let's do that. So again, we're assuming one box is 1 integer size. So we're going to use up 3 of them, 1500, 1501, and 1502. And we declare all of these as ints. And can anyone tell me what would happen to the values originally stored in these boxes? Yes?
They'll be jumped because your malloc is not malloc.
Yes. So, as correctly mentioned, since this is malloc, we do not initialize them to zeros. So these will all remain as junk originally, even when we typecast it as int. And we first initialize our value, which is 1500 here. So can anyone tell me what the third line x1 would be? Yeah? Zoe, can you repeat that? Correct. So this would be 1502. And finally, we have our third initialized x being our first element, but we add 2 to it. So this would be x plus 0, which is just whatever's in here, and we point to it, so 1500. Does anyone have any questions at this point right now? Yes?
I thought that line would be the contents of x plus 0.
Yes. So recall that originally these 3 boxes would be an array with int pointer types, right? So x2, it is saying that we point to x plus 0. So x plus 0 is just 4 plus 1, right? Okay, yeah, so what's happening is that our x is initially stored at 401, and we're increasing it by 0. So we remain at 401, and we point to the constants that's stored inside 401. So what's inside 401? 1500. So therefore, our box here would be 1500. Yeah? X, recall, this is our memory address. So x is 401. So I think the confusing part here is that this is an int pointer array. So the arrays, what this is holding are pointers from the dynamically allocated boxes here. So when we have 401, it contains a pointer, an integer pointer. So it's containing the integer pointer stored here. And then 1502, that's the memory address of whatever is stored here. Okay. So now we move on to, we both declare and initialize our P and Q. So can anyone tell me what P and Q would be? So our P would be here, our Q would be here. This is int a double pointer, and this is just a regular pointer. So can anyone tell me what P would be? Oh. Yeah. Yes. So this would store 401, and this would store 1502. The reason being is that when we say x, even though x is an array, when we make that equivalent to x, what that means is the memory address of the first element. So the memory address is 401, so that will be 401 here, and our q would just be pointing to x plus 1, which is just x plus 1 is 402, so we point to whatever is inside this memory address, so it's 1502. So we have 1502 here. Okay, so in the next line we have a double pointing of p minus 1 is equal, yeah? Yeah, so the reason why q is 1502 is because originally we have x. Our x is 401, right? So x plus 1 would be 402. Sorry? Okay, you understand? Okay. So, yeah, starting with this line, we have a double pointer to p minus 1 is equal to 100. So, can anyone tell me where 100 would be stored? So, we have at p of whatever is inside here minus 1, that's equivalent to 100. So can anyone describe what our line is doing? Okay, so what's happening here is that we have our p being stored at 404, right? So when we point to p minus 1, and what happens is that our p is stored at 404. So what happens is that we have 401 as what's stored inside 404. So we look at what's happening at 401 minus 1. So 401 minus 1, that's 400. So whatever is stored inside here. And what's this telling us is that we have some junk that's stored in here, and what's pointing to that would be equal to 100. So let's say that we have some junk here. Whatever is pointing to that junk would become 100. So this is also where our question 1 is being asked. So can anyone, our question 1 is saying, true or false, when a computer runs the corresponding line, it could cause a program to crash. So can anyone tell me if they think this is true or false? You have that.
This is true because we don't know if the memory address at 400 is outside of a program or not.
Yes, so what happens here is that we're possibly accessing an invalid memory location. This is because it's stated in our program that our main is using our boxes 401 to 1014. We do not know what's happening at box 400. This, it could interfere with another program, or it could cause where another function is stored here. So this could cause errors that could occur. Okay, any questions about that? Yes?
The little pointer, it takes the pointer that points to address 400 and uses that to keep
Yeah. Yeah. So then we proceed with the next line, p equals p plus 1. Well, in that case, this will just point to 402. And then, to the line from here, the pointing of q minus 2 is equivalent to 5. So can anyone tell me what would happen in the memory model when we run that line? Yes?
box 14, 403, right
Sorry?
So just take the address, so 45, subtract 2,
Yeah.
3, just go inside the contents, overwrite it.
Yeah. So as mentioned, we look at what's in Q, 1502. We subtract 2, and then we have 1500. So we point towards the 1500, and whatever is stored inside here would be equivalent to 5. So now we finally initialized our dynamically allocated box here. So the constant that's inside memory address 1500 is 5. Then Q equals Q minus 1. This becomes 1501. And now, line before our second question is at Q is equivalent to the pointer of Q minus 1 plus the double pointer of P plus the pointer of X at its first element. So that is a lot in one expression or one equation, and you will have to digest this. So let's first start off with the left side of the equal sign, so at Q. What is at Q? At Q is 1501. So whatever we're setting to be equivalent will be stored inside 1501. So a junk value here would be the equivalent to whatever's on the right side. So can anyone tell me, let's start with the pointing of Q minus 1. Can anyone tell me what the value of that would be? Yes? Yes, it will be 5. Because when we have Q minus 1, that is 1501 minus 1, which is 1500. And we point to the content that's inside 1500. So that is 5. So our first part, pointing to Q minus 1, that will be 5. Okay, how about a pointer to pointer of P? Yeah. Sorry? So let's look at what P is. So P is 402, right? So we point towards whatever's inside 402 first. So our value pointing to 402 would be 1502. And then we point inside whatever 402 is, which is okay, I made an error here. Okay, imagine this says P minus 1 instead of P. Okay. Okay, my bad, guys. So this would be P minus 1 instead of P. Okay. Yeah, so instead of, because what happens if we do P originally is that we have 402. 402 is here. We point to whatever is in 1502. So that would be junk, but that's not, yes?
Can we go to 1500, then go to 5?
Yes. So when we have P minus 1 instead, so I should probably write that down here. So instead it will be P minus 1. So we have 402 minus 1, so that's 401. We point inside 401, that's 1500. Then we point to 1500 again, so whatever's in 1500, so 5. So we have 5 plus 5 plus whatever is pointing in x of 0. So that is also 5 because x0 is 1500 and we point to the content that's inside 1500. So we have 5. So in total we have the contents inside this locker is 5 plus 5 plus 5. Yeah, my bad, guys. Just pointer of P minus 1. So this will be 15. Does this make sense so far? Yes? What would happen is, if it's just P by itself, is that it would typecast whatever's in here into an int and add it. We don't know what's inside here, so I can't give you a straight answer, but it will be 10 plus the whatever the integer cast of this chunk would be. Sorry? It won't crash because we dynamically, we're holding this memory in our dynamic allocation. So, yeah. Any other questions apart from that? About how I got any of these values? Yes? This thing here? Okay, so P is here, right? So when we have P, we have 402. That's what's inside this locker. So when we have P minus 1, that is 401, right? So right now what we're asking is pointer of 401. So we look at our 401 locker, and we point to what's inside 401. That is 1500. So when we do pointer 401, this would be 1500. And then we point to 1500 again. And when we point to 1500, we have this value that's stored here, 5. Okay. So now, any other questions? I thought I saw some hands earlier, but no? Okay. Okay. So we start off with our final line, our final paragraph of code. Oh, there's a question up there? Sorry, can anyone keep it down? Can you repeat your question again? The box 400, why is this what? Because we didn't declare or initialize anything in that box yet. So if you look at the beginning of our code, we start our main with using lockers from 400 to 1014. And our declaration of X starts at locker 401. We never use 400, and more importantly, as stated in the beginning line, 400 is not in our main function.
So aren't you setting it to 100?
Yes, so what happens in this line here, the pointer P minus 1, is that we're setting the junk that's stored here, we're pointing this, whatever points to this junk, would be equal to 100. And as mentioned in question 1, this could probably cause an error because it is not reserved in our memory. So if you run this on a computer, you could get an error here. So, yeah. Does that answer your question? Yeah? Sorry? Can everyone keep it down for a little bit? Yes, can you repeat your question?
Since we created 3 boxes using
Yeah?
are they considered, do we have to draw a box around them, or do we just
You could, it's not necessary because when we say we use up 3 boxes, we can just choose 3 boxes and just label them as int. That's the thing you should definitely do is write down int for your 3 boxes. I guess you could draw a box around them if you want. Okay, moving on to the next line. So now we store a string in locker 1009. So using the so this is a saw array. Let me just write it down here. And this is y. So this will originally contain the character A, the character 4, and the character 8. So then we proceed to our next line. Can anyone tell me what the next line does? So here. Okay. Yes?
Like in box 1013, you will like put up 5.
Yeah, so what we do is we check what our x address is. So x is 401. So we point to 401, which is 1500. And then we point to that again. 1500, we point, whatever's inside 1500 is 5. So the double pointer of x is 5. This is shown here. This is the same as if we replace x here. So we have 5 minus 1 is 4. So y of 4 is the string delimiter. So this here would be the delimiter. Okay, so question 2. Yeah, this. Could you speak up a little bit? In this line here, you're saying this would be a delimiter at the. So okay. Yeah, so there's a delimiter here. That's a good catch. You can throw candy here. Okay, yeah, so as correctly pointed out, this here would be the string delimiter because sort of A48 would contain, it will put a delimiter at the moment we finish the character A48. Right after 8, there will be the string delimiter. So in that case, our question 2. Okay, our question 2, would this be true or false if we print the string at y? Yes? Yes, it will be true. So as mentioned, the string delimiter here will print only up until we reach the string delimiter. So this would be A48. Yeah, my error, this is wrong. It's not, this is incorrect, yes. So it should be true. Okay, and in our final line, at the double pointer at p plus 1 is equivalent to the pointer at q. So can anyone tell me what the last and final line will do of this program? Okay, yeah. It will become what? 1501? So this box? Yeah? It will be 1501 instead? Okay, let's check. So in pointer of p plus 1, so we have 4, 2 is our p. So write this down here. So p is equivalent to 402. So p plus 1 would be 403. And we want to get the pointer of that. So the pointer of 403 will just be 1500. and then we get the pointer of that again. So the pointer of 1500 will be 5. So we have the pointer p plus 1 of 5, and then we want that to be equivalent to the pointer of q. So the pointer of q is just 1501. So whatever is in the locker here, 1501, we point to that. So the pointing of 1501 would be 15. So what happens here is that this will replace the variable here to 15. Okay, yes? 404? Okay, yeah, so what happens here is, this would be 402 here, right? So when we do 402 plus 1, it will be the memory address 403. Whatever, okay, so P is just the thing, that's the contents that's inside this locker. So that will be 402. And when we add 1 to that, that will just be 403. So we have P plus 1 is our 403. And then we point to 403, which is 1500. And we point to 1500, which contains this locker here. So, okay, yes? Yeah? Can you speak out a little bit louder?
Yeah, so why did you not include the delimiter in 1014?
1014? Okay, so originally I had this wrong. There should have been a delimiter at 1012. There does not need to be a delimiter at 1014 because when we declare a character array, we have A48, and then what happens in C syntax is that the character after ending character 8 would be the string delimiter. Okay. Okay, yeah? KC class. 101. Can everyone keep it down for a little bit? I can't hear another student's question. Yes? Why is this not? What about that? What is he saying? Oh, it's just junk. We'll get, yeah. Okay, and yes? So you're saying we have P is ours 402, right? And then we add 1 to whatever is in the content here. So P is not an array. So what happens is, if this was an array, for example, if this was X, then when we say something is equal to X, we refer this to as point of the address 1401. But this is not an array. This is a variable type. So it's P. So when we say P, we store whatever's in here and we add 1 to it. Sorry? It's a double pointer. So that would just be, we get the content that's in here, add 1, and we point to whatever's in 403 So 1500, and we point to 1500 again. So we get our value here. Does that make sense? Okay. Yeah. Okay. We'll move on to the next section now. Okay. Binary search tree. We loop binary search trees now. So, is this a valid BST? Yes? Why not? Yes. So our 6 is to a value node of 6 is not less than 5. So whatever node here is to be greater than 5. Okay. Is this a valid BST? Yes, it is a valid BST. Even though it's not balanced, it's technically a linked list. It still follows the condition that 8 is greater than 5 and 100 is greater than 8. So it'll just be a linked list in this case. So yeah. So suppose we are creating a BST with deletions. Okay, so I want you to draw out what the BST will look like when we insert the following. 5, 7, yes? Shall we? Yes, 5 is our root, so our key values are the integers here. So, yeah. When we insert the following nodes. Yeah. So I'll give you guys like 1 minute to draw it out, and then I'll take it off. Okay. So we initially start with 5. And then what happens is that we insert 7. We insert 7 to the right because 7 is greater than 5. And then what happens is we insert 2. 2 is less than 5. So we insert that here. And we insert 3. So we look at our current tree right now. 3 is less than 5. 3 is greater than 2. So we insert 3 here. Then we insert 10. So 10, we start looking at the root node. 10 is greater than 5. So we recurse rightwards. 10 is greater than 7. So the right child of 7 will be 10. Finally, we insert 4. So 4 is less than 5. Then we check the current node 2. 4 is greater than 2. So we go right here. And then 4 is greater than 3. So we make the right child of 3 4. And then in our final value 1, we check within our root node. 1 is less than 5, and 1 is less than 2. So the left child of 2 is 1. So yes. Okay. Could anyone tell me what the post traversal of this tree would be? Yes?
1, 4, 3, 2, 10, 5.
Correct. So our post traversal would be, as mentioned, 1, 4, 3, 2, 10, 7, and 5. So the reason why our post-reversal works like this is because how this works is that we always recurse, so we just go like BST, root arrow left, then BST, root arrow right, and then we print. Okay. So what would be the pre-order traversal of this tree? Yes? Correct. So the pre-order traversal would just be the following, and the difference is we place our print at the beginning. So this, the benefits of pre-order traversal is that this is good for when we want to copy down a tree. Okay. So I'll just take this up right now. What will the BST look like when we remove 7 and then 2? So if we remove 7, in that case, it will just, we only have one child node. So it will just point to 10 now. Okay, so can anyone tell me what would happen when we delete 2? Yes? So what would our successor be when we get, will be 2? Yes. So when we have 2, we notice that we have 2 children here. So we want to get our lowest most node in the right subtree. In that case, our smallest one is 3. So we replace 3 here, and we delete it. So this would be, we replace this with 3, and then we originally had our 4 here. So this is how the subtree, this is how the tree would look like now. So any questions about this? Okay. What time is it? Okay. I guess I'll give you guys 3 to 4 minutes to write down code for this question, and then, yeah. Hey, sorry?
It's almost 6. Maybe I'm getting too concerned about the time. If you want to even like let me finish off BSTs, if you want to break or something, it's almost 6. It's been like an hour.
Okay.
It's up to you. If you want to.
So we just skipped the final question? Like,
What?
there are 2 questions. Just one more.
Then maybe I'm getting too concerned about time. Like, you think you're good? Do you want to do the other one as well, or you want to just like call it there? It's up to you.
Let's just finish it off. I won't. Yeah. Okay. Okay, so I'll take it up now. Okay, so we always start with, whenever we solve a question involving VSTs, we always consider the case where the root is null. So if root is null, then we just return 0. Then what happens is we should check what happens at the leaf node. So we know a node is a leaf node when it has no children. So if the left child is null and the right child is null, we just return the value of the node. Okay, and then as a recursive step, we just return the sum of leaves of our left child and the sum of leaves of our right child. In essence, this would get the sum of the leaves of the left subtree of root and the sum of the leaves of the right subtree of root. Okay, any questions about this? Yes?
What about the value of the root itself?
Sorry?
What about the value of the root itself?
Value of the root itself? Well, the thing is, if we want to look at the value of root itself, that would mean, if that's included in our sum, that would mean our root is a leaf node by itself. So in that case, it will just, there won't be any recursion. It will just go to a second else if statement. The left child is null, the right child is null, we return root.val. The reason, and anything else, any other case where we have a child of root, we don't include that in our sum because root is not a leaf node anymore. Yeah. Yeah. Okay, so let's look what happens when we have a root. So let's do a first case when it doesn't have, if it's just a single node. In that case, what happens is that we skip the first statement because we have a root. We have no child in the left and no child in the right. So it satisfies the second statement, else if statement. So we return the value that's stored here. So like, for example, if it's 5, we return 5, and the function terminates. So any other case, if we have a single child node, what happens is that we immediately proceed to, it skips all our if statements, just a recursive step. So we return the sum that is here. This is null, so that's 0. The sum that's contained in this left subtree. Sorry, the right subtree. Because we don't include this in our sum because it's not a leaf node anymore, or child node. Yes?
In the return missing, are you, like, in the return statement, are you missing, like, root L file? Because you're just adding the left subtree, the right subtree, not root subtree.
Okay. So we only include this. So there was 2 questions like that. We only include the root itself if it is a child node. We're only adding up nodes that are leaf nodes. What a leaf node is that it has no children. If we included, we can never have a statement where we have the sum of this and this exists. We have a right child. But we can never include a sum here because we know there's a child here. We're only adding up leaf nodes, not any other nodes. Okay. I'll move on to the next now. So find the difference between the smallest and largest value in a BST, and we can assume that the root is non-empty this time. Yes? It doesn't assume so, so you don't assume it's balanced. It doesn't say so anywhere, so yeah. Okay, so I'll take it up now. So we want to find the difference between the smallest and largest value in a BST. So, for example, if we use this BST, first we want to locate where our smallest and largest values are. So can anyone tell me where would the smallest and largest values be in a BST? Yeah, okay. So we look, our smallest values is the leftmost node, so we keep traversing leftwards, and that would be where our smallest value is located. And for our largest value, we keep traversing rightwards. And then those were our two extreme values will be located at. So how do we find both those values? So we can have two helper functions. One for BST min. So this would keep traversing leftwards, and if our left child is null, that means we found our smallest node. So for example, if we have 5, then left child is not null, so we keep traversing, we return the function again, then we return the function again, and when our left child is null, we found our smallest value. So return root arrow out. Then likewise, we do the exact same thing for BST max. So we keep traversing rightwards, and when our right child is null, we know that we are at the node that contains the largest value in the BST. So does that make sense? Oh. Okay. Yes?
Would looping be a better solution, or
You could also loop in it. I guess looping would preserve memory, but time complexity wise it would be the same. It will still be whatever the length of the left branch would be and whatever the length of the right branch would be. So time complexity wise would be the same. Running a for loop would be better memory wise. Okay. So then we finally can use our function now, and we just return the difference between the two, max and min. Any questions with this? Yes? Sorry? So can you repeat your question? I can't hear you here. Okay, so we're not returning values at the up of the stack, so this won't be tail recursion. Okay. Any other questions? Yeah. Sorry. Can you speak up a little bit? The root is null. No. Well. Okay. So. Okay. Yeah. Yeah. So I can't. Yeah.
Can you repeat why the first two functions won't be tail recursion?
Wait, can you answer her question? Oh, is this tail recursion?
Yes.
Okay.
So the individual min and max functions are tail recursion, but the actual BST difference is we call it two separate functions, and it's obviously not calling itself. So the helper functions are tail recursive, but the main function isn't.
Okay. So any other questions? And if not, we'll take a 10-minute break. So yeah. Okay.
We're going to continue on. So you can get to your seats. We're going to move on to graphs. So yeah, it's favorite part of A48. All right. So just going to do a quick review. So can anyone tell me the difference between a directed and undirected graph? Yeah. Right, so just to kind of put it in more technical language, so an undirected graph can have something like, if you have two nodes A and B, then in an undirected graph, if there's an edge, it's got to go A to B and B to A. Whereas in a directed graph, you can kind of have something where A goes to B, but not B to A. So yeah, and then what are two ways to kind of represent the information in a graph? That's probably a better term for that. Yeah. Right, so it's an adjacency list and an adjacency matrix. And we're going to kind of go over that in a second as well. And then kind of a bit of another question. So we have the following statements. So those kind of symbols mean vertices and edges. And so that's kind of saying the number of vertices is always less than the number of edges. So is that statement going to be true for any graph? Maybe just kind of like a show of fingers. Yes, it's true. No, it's not true. No. Seeing mostly thumbs down, and that's right. And so the reason that is because we can always have nodes that just don't have any connections, right? So yeah. All right, so kind of moving on to traversals. And so the difference between depth first search, breadth first search. Sorry, give me one moment. And I'll just kind of go through it. So BFS is going to kind of traverse level by level. And a DFS is going to exhaust one path before it tries a new one. And so I think kind of, again, you'll see an example in a second. So suppose we have this graph over here, and we do some search, and the nodes that we encounter are going to be in that order. And so do you guys think that this is going to be a depth first search or a breadth first search? And I think while you guys think about it, I'm just going to write it down on the board. Here. Okay. All right. I guess kind of same thing. You can do maybe a 1 if you think it's a DFS, and a 2 if you think it's a BFS. So, oh, whoops, what happened? Oh, there we go. All right. So I think 1 was DFS, right? So yeah, it's going to be a DFS. And just to kind of explain kind of briefly, so first node that we're looking at is a 0. So assuming we start here. And then the next node we check is a 2. And so if this were a DFS, we would maybe check something like all of its neighbors first. So in this case, it would be 2 and 4. I actually think the one I have, oh yeah, no, so 0's got 3 neighbors. So we're checking 2, 4, and 5 first for a BFS. But you can see for the DFS, we're checking 2 and then 3. So we're kind of going to 2, and then we're exhausting this path. And then we're going to the next path and then exhausting it, rather than kind of going one level by level. So yeah, there we go. And then kind of a bit more, I think this is the same graph. We have this kind of graph here, and mentioned before, there's 2 ways to represent it. We can use an adjacency list or a matrix. And so how would you kind of represent that? And so I can give you guys maybe a minute to write it down. Yeah, I think I'll draw the grid in the meantime. Let's see. All right, so I'm going to start with the adjacency list. Let me just double check. I think it's right. With an adjacency list, we want to kind of represent, for each vertex, we want to represent the list of vertices that it's connected to through the edges, right? And so we can start off for 0, for example. We know that it's connected to 2, 4, and 5. And so we can correspondingly just say that 0 is going to go to 2, 4, and 5. I know I'm writing it as a list here. Pretend it's a linked list, which is kind of how we would typically represent this. And I can kind of just continue this for the rest of the graph. So for 1, we know that's going to go to 4. And for 2, 2 is only going to go to 3. And for 3, we actually don't have any kind of outward connections, so this is actually just going to be empty. For 4, we're just going to 5. And for 5, we're just going to 1. Let's see. Did I miss anything? I think I did. Oh, yeah, sorry. For 2, this should be going to 3 and 4. Or wait. Yeah, this should be going to 3 and 4. All right. So that's kind of what we have here. And oh, you know what? That's actually wrong as well. I think I missed one. I mean, that 0 is wrong. But I'll fix that, I guess, after. All right. And for our adjacency matrix, we are going to kind of represent the same information as a matrix, right? And so this is going to kind of say this vertex connects to this vertex, right? And so we'll start with 0. So we know that 0 is going to connect with 2, 4, and 5. So we can kind of just put our 1s over there, and then everything else is going to be 0. And then for 1, we know that this is going to connect to 4, and then we could put everything else as 0. For 2, this is going to go to 3 and 4. For 3, this is going to go, again, to nothing, so this whole row is just going to be 0. And for 4, this is only going to 5, so this one's going to be a 1 here. Everything else is going to be 0. And finally, for 5, we're only going to 1, so we're going to put a 1 here, and everything else going to 0. Right? So wherever there's an edge, we're going to put a 1. Wherever there's no edge, we're just going to put a 0. Are there any questions about that? Nope. All right, yeah, pretty simple. So, yep, so we can move on. All right, so we're kind of on to our questions now. So, first question is, suppose we have a directed graph represented by an adjacency matrix with V nodes. And so here we're only going to write in pseudocode. I'm not expecting, typically with these kinds of questions, you're not really expected to write full code. So just pseudocode is good enough. And so we just want to determine the total number of edges on a graph. So I'll give you guys a couple minutes. Remember, we're using an adjacency matrix.
All right, I'm going to take this up. All right, so does anyone have any ideas on kind of how to approach this problem? Yeah.
For each row in the adjacency matrix, then we could check like for each column in the row.
Right.
Then like check, then like increment the counter variable by the index, like by the number in the matrix.
Right.
And you could like divide by 2 so that
Okay, so
because you would have duplicate, like, I mean you're counting the edges 2 times.
right, so but if we have a directed, okay, so so the suggestion I got was essentially to count, go through the matrix. So if we kind of look at this as an example, we're going to go through each row, we're going to go through each column, and we're going to essentially have a counter going to see how many edges we have total. And then after that, we're going to return the counter. The suggestion was to return it divided by 2. So this is like 90% of the way there. The only reason why I would say maybe we don't want to divide by 2 is because we're dealing with a directed graph. So when we're dealing with a directed graph, let's say we have 2 nodes, or 2 nodes that maybe are connected to each other like this. We would consider those 2 different edges. Because this edge doesn't necessarily imply this edge, right? Because it's directed. But that actually leads very well into the next question, which is, oh, whoops, wrong one. Which is, what would happen? What would we change if this was undirected, right? We would just return edges divided by 2, and that's the exact same result. Or I think what I wrote down here is we can kind of break down the problem as counting the amount of 1s in this matrix. Because each 1 here is going to represent an edge. But we know that for an undirected graph, that this is going to be symmetrical, right? And so we don't actually have to loop through the whole graph, or the whole matrix. We only just have to loop through 1/2. And so the way we can do that here is just in our loops, we can just say, make sure I is less than j, right? And that just kind of saves us a bit of computation. But if you were to say return edges divided by 2, that's kind of an equally valid way to get the same result. All right. So moving on. Are there any questions about this? Nope, perfect. OK. So moving on. We've got kind of this mystery function. And so we can, again, assume graph is represented by an adjacency matrix. It's unweighted. And then what does this function do? So you can, again, look at it for a minute, try to figure it out. Yeah, and just assume num nodes is just some constant representing how many nodes there are in the graph. Yeah.
It turns a directed thing into an undirected thing.
Right. OK. So that's right. So what I heard was it's going to turn a directed graph into an undirected graph. And so that's the answer. And the reason that's the case is, again, I can kind of, again, use this graph as an example. And so what we're saying is that for any time we find, so we're going to loop through everything in the matrix. And we're going to say any time there's either a connection from I to j or j to I, we're going to set both of them to 1. And so what that's saying is, let's say this one, for example, this connection from 0 to 2. When we get there in the loop, we're going to say, if there's a connection from 0 to 2, then we're going to set the connection from 0 to 2 to 1, but also 2 to 0. And so we would essentially be turning this into a 1 as well, which is the same as saying putting an arrow here as well. And so that's just, as we kind of repeat that for all of our edges, the result is that we're going to get an undirected graph, right? Those arrows are kind of redundant in an undirected graph. I'm just putting it there for clarity. All right. And then any questions about this? All right, perfect. All right, and so last question, a little bit longer. And so here we're going to get some we want to write some pseudocode for a function that we're given some starting node n in a graph G. And we want to say all the nodes that are not k steps away, we want to take their sum. So it's a little bit, I can kind of use this graph as an example, even though I just made it directed. So let's say, sorry, give me 1 second. Let's say we have, let's say like this is our graph, for example. And so let's say our starting node is 2. And we're going to say k is equal to 1. And so we're going to say return the sum of everything that is not 1 step away, or the node itself. And so in this case, we're going to have 1 step away is going to give us 2 itself. We're going to get 4, and we're going to get 3. Right? And so in this case, we would want to return the sum of everything that is not one of these nodes. So we're going to get 5 plus 1. And so for that specific, for those parameters, we would return 6. Right? And even I'll kind of give you guys a little bit of a hint. So for this one, I use some helper functions. And so kind of the helper functions are to get the sum of the graph, to get all of the nodes that are attached, and then from those 2 helper functions, get the result. And so I'll give you guys a little bit longer to think about this one. But yeah.
Sorry, but are we assuming the ID of the node is the value?
Oh, no. So that's, yeah, I can see the confusion there. That was more an example of just like using the ID as the value. But again, I didn't actually kind of define the structure of the actual node itself. So you can kind of, I don't want to say make it up, but like you can kind of maybe infer what a suitable name would be. The whole point is that because it's pseudocode, it's supposed to be more general and vague and more suitable to more kind of, for example, if you were writing this in different languages, you would want to be able to use that pseudocode for those different languages, right? So we want it to be very general. So yeah, that's kind of why those decisions were made. But yeah, I understand the confusion. It is directed. Sorry, I should have mentioned that. Yeah, it's directed. Okay, that's a good question. So for this res parameter in the second helper, again, you don't kind of have to structure it this way. This is just the way I did it. That's a way to just store the result of your all the nodes that are within k steps of n. So I mean, I called it result. Maybe a better name would be like kind of nodes, or just like nodes that are attached. Yeah. Sorry? Yes. G is the adjacency matrix. Yep.
Do you have access, like the indices, like how many indices we have for our matrix?
Yeah, so again, this is just pseudocode, so we're not too concerned about making this like C code itself. So you can just say something like g.size or g.nodes or something. Like, it doesn't actually matter what the individual values are called, but we can assume that we have access to at least how big the graph itself is. All right, I know some of you guys are still working on it. I'm going to kind of start to take it up. I mean, I'm going to just go one helper at a time, so you can still kind of maybe think about the problem in the meantime. At the very least, I'm just going to go over that first one, just I guess to get a sense of how the pseudocode is laid out. So I guess I should say kind of the general goal of setting up my functions this way is to say we want to get the sum of every single node in the graph, and then we want to just subtract everything that's within k distance. And then the result of that is that we're going to get everything that's not within the k distance, right? So yeah, I guess I can just go to the first function. And so here, we're just going to add up every value in the graph. And this is pretty simple. So we're just going to say, let some value sum be 0. We're just going to loop through every node in the graph. And we're just going to add the value of that node. And so again, this is what I mean by the kind of attribute names and variable names are kind of very loose. It's just supposed to give an idea for if you were to program it, kind of how you would at least start and say how you would maybe implement it in more language-specific ways. And so, yep, we have sum plus equals val. And then from there, we can just return the sum. So that's kind of relatively straightforward. We're just going through each vertex, and we're adding up the value. And so now for this get all attached. And so first thing we want to do is our base case. And so we'll say if the depth is 0, we can just return. And actually, maybe I think there's a slight mistake here. We should actually be adding the node itself if the depth is 0. I guess it depends how you define depth of it. If a depth of 1 is including the root node but not other nodes, the way I kind of defined it before would imply it's otherwise. So I'm just going to kind of take back a little bit and say that a depth of 0 means kind of nothing, and then a depth of 1 means only the node itself. I think if you change that to a -1, it would kind of push that one value back. Yeah, it just depends how you define it. It's not very clearly defined what a step is. So there we go. And then next thing we want to do is loop through each neighbor of m and n. And if you want to think about kind of more specific implementations, then you can think maybe if it was an adjacency matrix, that would be equivalent to looping through a row. Or with an adjacency list, that's the equivalent of just going to one of the linked lists. And once we have each neighbor, we can just say if m is not in the result, then we can add m to the result. And so here, we're just kind of collecting all of the neighbors of m. And then, oh, actually, I think there's a bit of a mistake in my pseudocode. So what it should say here is instead of just returning all attached, we want to loop through each value for each neighbor. We also want to get all attached for each node stemming from there. So that should be an m instead of an n, and it should kind of be 1 indented. But again, the idea there is that we're essentially saying, let's start at maybe 2, for example, maybe with k equals 2, and say, all right, we're going to add this node. We're going to add all the neighbors. And then for each of the neighbors, we're going to run that same code, but with k equals 1. Right? And for k equals 1, same thing. We're going to add everything to the result by kind of looking through all of the neighbors. And then from there, we're going to see, well, here we have a neighbor. These two we don't have a neighbor. So the next step would then be to kind of go to this node. And when we're running the recursive call here, that's going to be at k equals 0. And remember, that means we've hit our base case. That's the word. And so then we're going to stop. And then at that point, because we've already added everything to the result, when we return the function, the result is all of these nodes.
How is 1 added to
That was 1. Because when we're here, when we're at this 4, we're adding all of the neighbors. So it might make more sense to kind of restructure the code as to say, add itself and then run the recursive call on its neighbors, rather than add the neighbors and then run the recursive call on the neighbors. So that kind of might make more sense in retrospect if I were to rewrite this. Yeah.
How does that work for like a matrix?
So we're just kind of going through each row, right? So each row, let's say we're starting here. So first thing we're going to do is look through 2. And then we're going to say, all right, add all of the neighbors. So we're going to loop through the row and add all the neighbors. And so now all of these guys are now stored in my result array. But now for each of these neighbors, we're going to do a recursive call. And so on 0, we're going to do the same call. On what are the other neighbors? 3 and 4, we're going to do that same call. But this time, we're going to do it with a depth of k minus 1, so that we're not just going forever, right? Yeah?
If we do it like that, do we check if m is already in the result list, or can we just do the recursive call?
So the reason that we're checking if m is in the resulting list is because we don't want duplicates. So for example, if we have maybe 0 goes to 2 and 2 goes to 0, then what happens is, let's say we start at 0, and then, OK, we're going to get all of its neighbors, and then one of its neighbors is 2. Now we're going to get all of 2's neighbors, but now we're going to check 0 again. And so the issue with that is that we end up adding multiple nodes, multiple of the same node, to the array. And then it also makes it more inefficient because we don't want to have to do those additional calls. Yeah? Yeah, so to reiterate, the mistake is that we are not calling the recursive call on the neighbors. So we want to say to get all attached of m, not n. And that's within the loop. Does that make sense? Yep. So, yeah, so what would happen with this code is it would essentially we wouldn't really be like traversing anywhere. All we would say is we're starting here, we're going to find all of our neighbors, but we're going to make a recursive call to the same node. And so we don't want that. We want to traverse across our graph. Yeah?
So basically with this function, you're trying to get all the nodes that are accessible.
Yeah. So this is, the term for this is breadth first search. And again, there's different ways to do this. So if you did this using a depth first search, maybe using a kind of a different kind of helper function, that's equally as valid. But this is, again, just the way I chose to do it. Especially with pseudocode, there's many right answers. And so this is just an example of actually a wrong answer because I messed it up. But yeah. Oh, sorry, is there a question in the back? No? Yeah.
Sorry, so for the recursive call inside the AMACSS, you not have to change the input node instead of changing to its neighbor, right? Otherwise, you would always be looking.
Yep. So the recursive call should have the node be its neighbor and not the initial node. Yep. Oh, yep. Yeah, if it wasn't in the if statement, then we would make the call if m was a duplicate, right? So we don't want to make that recursive call if it's a duplicate. Yep.
We would do it to m's neighbor, but like, how would we, given what we are doing, like, how would we know which neighbor to?
How would we know? Sorry.
How would we know which neighbor to like call, like use when calling the function?
So like what, how do we know which neighbor it would call first, essentially, like the order? So we kind of don't. Like the order doesn't really matter, right? Because again, kind of going back to this example, if we check maybe 3 then 4 rather than 4 then 3, we should still get the same result because these are both neighbors of this initial node that has a depth of k minus 1, right? And more practically speaking, let's say in an adjacency list, right? The order of this list just happens to be whatever order we added these edges, right? And so if this maybe 4 and 5 were swapped, that shouldn't change the actual functionality of this function, right? OK, I think I'm going to move on. If there's any other questions, you can ask me during the break. Finally, we have this kind of our main function, the sum of the inaccessible ones. So here, we're just going to initialize an empty list, and we're going to call our function. And we're just going to, again, return the difference of the sum of all of the nodes minus the sum of the nodes that are within k distance. And again, I kind of use that sum function pretty loosely. That's kind of one of the nice things about pseudocode is that I don't really have to worry about that, right? So, because maybe some languages have that functionality and others don't. But as long as it's clear to the reader, then that's all that matters. Oh, wait, where are my variable names? What is A and B? OK, I edited this a lot. It should say that the A is the sum of the graph. Or sorry, A is the get all attached, and B is the sum of the graph. Or no, sorry. Yeah. So wait, sum of graph should be G instead of B, and the sum should be res instead of A. Yeah, I changed how this function works a lot, and I still didn't get it right. So yeah, there we go. Not an easy question. But I think one that's more, again, with pseudocode in general, one that's more important to understand more conceptually rather than the individual kind of nuances of it. Yeah.
I like Rex. I feel like important function that would say like an array, like
Yep.
let's say G has like n nodes.
Sure.
Say like
For C, yes. Are you saying like in terms of the actual functionality of that kind of array? For pseudocode. Again, so if you think about a language like Python, you don't need to specify the length when you're calling something like sum, right? So when you write pseudocode, you can kind of assume that those language-specific details will be handled by the programmer. And so you can pass that in if you like, but it's not something that I would think is necessary. All right. OK, I'm going to move on. Oh, it's loud. I'm going to move on. Again, if there's any other questions, you can come after me during the break or after the seminar. And we're going to move on to complexity. All right. So, we talked about a little bit this in the midterm as well. So, just kind of a refresher. So, true or false, an algorithm that runs in O(n) time will always be slower than an algorithm that runs in O(1) time. So, is that true or false? And yet, thumbs up, thumbs down. What do we think? Seeing pretty much all thumbs down, and so that's true. And the reason is because we only care, big O only tells us how a function grows with the input size, not how fast it is initially, right? And so here kind of just a quick kind of like matching the algorithm to the complexity. And so if you have, we say those are arrays, I think more used to Python. So if you were finding the mean in a sorted list, finding the median in a sorted list, finding the median in an unsorted list, each of those kind of algorithms can match up to a different time complexity. So does anyone want to kind of try their hands? So at least for that first one, which time complexity is that going to match to? So for finding the mean in a sorted list. Yep. O of n, right? And the reason being, because we have to loop through every element in the array to find the mean, right? And so the next one, finding the median, so the middle in a sorted list. So what's that going to be? Yep. O of 1, yeah. So that's going to be O of 1, because if the list is sorted, then we can just take the middle element, and that we know in array access is going to be O(1) time, right? And then finally, whoops. I don't need the screen or the mic, apparently. So the last one was finding the median in an unsorted array. So that kind of just leaves us with that last one, which is n log n. And the reasoning for that is that we have to essentially sort the list to figure out what's the middle element, right? So yeah, all right. I don't know what happened here. Something unplug? No. It's finicky. If I just shake it a little. Excuse the technical difficulties here. Yeah, I don't know what the setup here was. Did the whole thing just shut off?
The whole thing, because it's also a mic.
Yeah. Like the whole setup just shut off. It wasn't even just our. What the hell? All right. We're going to take a quick break. I don't know what happened. We're on the case. We're figuring it out.
Can you just skip the question with the one that reads actually on? I don't think
Yeah. No, I was going to skip some of these anyway. It was the whole screen shut off. Like, I don't know.
Is this system now?
And I don't know if it's a coincidence. It happened like right at 7. I don't know if they shut it off or something.
Because the lights flickered as well. I don't know if you noticed.
Oh, was there like a power outage?
Yeah, probably. Only for like a second though.
Yeah, but the whole thing shut off.
started?
Is Mel hard? Keys.
Yeah, let me go try to find someone real quick. I'll be back in.
Yeah, sure. This thing is what? I don't know. All right. So it seems like there was some sort of like power outage because the whole system's down. We're trying to figure it out, but it might be a bit of time. Yeah, we are working on it. So. Wait, so this thing's actually just down. The projector is working. Yeah. Is there a way to connect direct to the projector or something? Like I'm thinking if is there a cord where you don't have to go through the computer? Like I don't know if this one is. But I don't think
I don't think it was connected.
We just pray for it to turn back on. Like what's the one other thing I'm thinking is you just kind of do the other hour online or something. That's actually worst case scenario.
Worst case, you can do that, or you can just say the questions.
Some of these you really kind of need.
You need the screen.
Some of them, yeah. This one not really, but some of them you kind of need it.
I've never seen the power.
Yeah. Can't migrate to a different room, right? No. No, you're right. I'm trying to think. We didn't book it, but we can just rob it for now. Kind of
I don't even know if the other rooms are working.
go around. So are other things on IC not working? Just this?
Either, I think the best.
We could call IT. Yeah.
Oh, okay. So we're kind of.
So, the options are try to continue the best we can with the slides, or the mic's not working. Yeah.
The other mic is running on that. Because I was thinking, even the projector's not working.
My voice is loud enough where I can do it.
Can I understand them all? This is the recording myself. So everybody can watch the video.
Yeah.
There's not really. Because if you try to teach them what complexity is without showing them all the
Yeah, no, impossible. It's impossible. Oh, we don't have permission. Marcelo. Oh, crap, okay.
We were about to ask you for the slide representation after.
Yeah.
You can migrate to IC240. I can run and see if it's about 10 minutes or 15. Then you guys can have
It's sticky, yeah. We're speed running it, and it's already
There's still 2 more after the section.
yeah. Well, they're shorter sections, to be fair, but yeah, these 2 sections are a little shorter, but and honestly,
The person is not that bad.
yeah. And then even some of these, I might be able to kind of because a lot of these are design a function, right? So this one I can do. This one I probably can't.
Okay, I'll go take a look at
Probably not that one. That one I definitely do.
some of them might
And also just moving everyone. Yeah.
If everyone moves fast,
That. I don't think it's 10 minutes. And also the system could be down in 224. I think we just move it to a recording. Yeah. Oh wait, no, like whatever. But I'm just thinking more in terms of like a 6 of like the recording itself. All right. Yeah. No. Okay. All right. All right. So it looks like the power's out and it's not coming back. So what we're gonna do is we are going to rush home and record the rest of the seminar ourselves and post the recording. I don't know what happened with IC, but it's gone. The whole system's gone. Thanks for coming, everyone. All right, everyone, welcome back to the recording. Again, we apologize for the technical difficulty, and we're just gonna kind of continue right from here. And so before we kind of get into it, I'm just going to go over this question since I know there was a little bit of confusion. So I've just kind of fixed up my pseudocode a little bit here, and I'm gonna just go over it. And so the main thing that changed, whoops, what happened here? Okay. So the main difference here is in this get all attached function here. And so the way it works now is just a little bit clearer. And so let's say I have a graph that looks like this. And I call this function with this graph, and let's just say as an example with node n equals 1, so we're going to call this node depth of k equals 1 as well, and our result list is just kind of this empty list. And so one thing that also I didn't explain super clearly initially was that this result list is kind of being passed between all of the recursive function calls. And so all of these functions kind of share the same list. It's almost like a global variable, except it's not technically, but that's kind of, if you want to think about it that way, it is kind of helpful to, visualize that the array exists outside of the function. So there's that. And so when we actually go through the function itself, what we're doing is we're saying, if we start at this node 1 here, we know it's being called with a depth of 1. And we're going to say if our n is not in res, which it's currently isn't, then we can add it to our list of res. And if k equals 0, which it doesn't, we return. This is kind of our base case. And then we're going to say for each neighbor m of n, right? Then we're going to call it on m, which means that we're going to call it for each of its neighbors. So in this case, 1's neighbors are going to be 2 and 3. And so when we call it, let's say it gets called on 2 first, it's going to get called on 2, but it's going to get called with k minus 1. So this is going to be k equals 0. And this is essentially telling it that we don't want it to have any more steps. And so when it gets called, first thing we do is we add it to our result list. Then we say k equals 0, return, and so it's done, right? Then we kind of go back here, and then we're going to make our recursive call on this k equals 3 guy this 3 node with k equals 0. And so again, we're going to add it to our result list, but since k equals 0, we're going to exit, and then we're going to exit the function, and this is our result. And as a reminder, the reason we do this check is to ensure there's no duplicates. So if our graph looks something like this with a depth of 2, we want to make sure that if we look at the neighbors, we are not adding it, right? Another way to kind of present this, it would be to do this in the get all attached. So if we were to, for example, ensure that the neighbor is not in the resulting node, that would also be valid. The difference is doing the check before or after. So yeah, and then here, I just kind of fixed a typo I made. Here we're doing the sum of graph of G, and the sum is of the result list, since now this result contains all of our nodes. And then another thing to clarify, when we're doing pseudocode, again, we don't care about a lot of the minute details of how the actual example, like how the sum function works. So we can just say that if we sum res, that I believe would be clear enough. All right, so I'm just going to move on to where we left off. Let me stop annotating. All right. Oh, there's one red dot left. Didn't clear all my drawings. There we go. All right, so we already did this in the review seminar. And so moving on to this, this title's actually wrong. This should just, again, from a previous version of the slides, it kind of changed around last minute. And so this, we're just kind of looking at the different time complexities of the various BST operations. And so here, when we're inserting into a balanced BST, that's going to be log n. Searching is also going to be log n. Deleting is also going to be log n. And when we're traversing, that's going to be n, since we have to visit all the nodes. And just for a little bit of context of why this is log n, when we're working with balanced BSTs, let me pull up my annotation. As the number of kind of rows gets bigger, we only have to search through kind of a certain amount, like we only have to search through, let's say this is k layers. We only have to search through k layers instead of n nodes, right? For traversing, let's say for n nodes, right? We have n nodes. But one of the things that we know is that the number of, so if we do 2 to the k layers, that's going to give us the number of nodes. And we can rearrange this equation to give us log base 2 of k is equal to n, which is where we get our equation. Oh, sorry, this should be log base 2 of n equals k. So log base 2 of n is going to be our complexity, right? And since we don't care about the actual base of the log, we can just write log. And actually this LG here, I believe that implies base 2 of a log. So this is a little bit redundant. So it's kind of how like ln implies that it's just the log with the base of e. LG is log with a base of 2. Right, so moving on. For the graph operations, I'm not going to kind of go over these too much, just because they're already covered in your notes. But I'm just going to refer back to this for a later question. And so the first question, this was something that we saw in the review seminar. And so we want to try to figure out what the complexity of this function is going to be if the BST is balanced. And so what we have here are essentially, we're calling 2 different functions. We're calling this min and the max. And when we look at the min and max, let me draw an example tree here. So this is an example of a balanced tree. So for the min, we're noticing that we're just going to the left until we can't anymore, since the min is just the leftmost node. And so we're going through the amount of layers that there are in our tree and not the amount of nodes. And so that's kind of a hint to tell you that the complexity is going to be log n instead of just n. And so we can say that this function has a complexity of O log n. And this function essentially does the exact same thing, except we're just looking at the right instead of the left. So this is also going to be log O log n. And so when we are dealing with this, we're dealing with two O log n operations. And so the final complexity is going to be O log n. However, is this going to be different when the complexity of the function, or is the complexity of the function going to be different when the BST is not balanced? And it is, it's actually going to be O of n. And the reason is when the BST isn't explicitly balanced, then we can almost just treat it like a linked list, since the worst case scenario for a BST is that it's going to look like this, right? Just going to be keep one node, one node, one node, one node, all the way, right? And so if we think about this BST max, that's actually just going to search through every single node in this tree. So this is going to be O of n, right? And when we have an O n, and then with this tree, this would actually be O1, but when we have an ON and O1 operation, that's going to give us ON. So we don't really care about the other one. Right, okay. So moving on, right to question 3, I guess. Assume a graph is stored as an adjacency list. Design a function, given an undirected graph, return a directed graph. And I'm gonna just let you pause for a second to try to figure this out on your own. I'm gonna reveal the answer, 3, 2, 1, and here it is. And so what we're doing here is we're saying that because we're storing it as an adjacency list, we actually have an easier time just creating a new graph rather than modifying the existing graph. Because if you remember, the time complexity of checking if two nodes are connected is O of v. And so if we had to do that for every edge, that would be that would grow with the number of vertices, which we don't necessarily want. However, when we write it like this, then it only when we add an edge, right? That's O of 1. So that's going to be much faster. And so what we're doing is we're saying, let's say we have I'm going to do a very simple graph. So let's just say 1 goes to 2, goes to 3. And so our adjacency list would look something like this, with 1 going to 2, and 2 going to 3, and 3 going to nothing. And so first thing we're going to do is create a new graph. So let's just call this maybe G1, call this one G2. And so we're going to set this up and say, all right, for each vertex in G, and then for each neighbor, N of V, so we're going to loop through each of these vertices, and then for each of the vertices, we're going to loop through each of its edges. And then we're going to say, to this new graph, add the existing edge and the opposite edge. And so here, this is going to add this edge, and it's going to add this edge. And then we can move on to our next vertex. So this 2 goes to going to 3. So it's going to add 2 to 3 and 3 to 2. And we can return our new graph. So this is what we return. And so now, the reason that we design a function like this is because of its complexity. And so the complexity of this, and again, you could pause if you want to think about it, but it's actually going to be O of V plus E, or the number of vertices plus the number of edges. And the reason that is, you might think that it's the vertices times the number of edges because we're looping through each, but the number of edges will, when we loop like this will just, both of these combined will actually just cover all of the edges. So this is almost O of E, except if we, for example, have a graph with maybe 1,000 vertices and no edges, then we still have to loop through all of those vertices to at least check if there's an edge, right? And so this ends up being O of V plus E. All right, and moving on. And there's question 2. Following algorithm reflects a BST at its root. What is the complexity of this function if the BST is not balanced? And so to kind of clarify what this function does, we're going to take a BST. Let's just say it's like this. And when we invert it, we're just going to flip all of the trees and all of the subtrees and all of the subtrees of the subtrees and so on. And so this would turn into, I should have given myself more space. So this is going to turn into this. So the root's going to be the same, except we're going to have a 1 and a 0 here. And we're going to have a 3 here. And one thing to note is that you could still treat this like a BST, but now the order is reversed. So now if you're, for example, inserting a new node, you would have to insert the smallest one on the right and the biggest one on the left. But as long as you kind of keep track of that change, then this could still work as a BST. And so, but we're not as concerned with that. We're more concerned with just the complexity of it. And so if we look at the function itself, we're kind of seeing that we are making a recursive call on the right and left node as long as the root is not null. And so if we think about that, that just means that this function is going to get called on every single node in our tree. And so we end up getting a complexity of O of n. And when the BST is balanced, then again, you can pause if you want to think about it, but that actually doesn't change the complexity because we still have to visit every node. And so it's still going to be O of n.
In this chapter, we're going to be going over recursion. So the first question, how are recursion functions structured and what exactly is a recursion function? I know you guys have already seen some recursion functions defined for BSTs or graphs, but to break it down here, a recursion function is a function that basically calls itself. How are they structured? It's structured into 2 different categories. One, it contains a base case, and the other part is the recursion case, where the actual problem is broken down into smaller sections. So here's the question. Are some functions only possible with recursion? The answer is no. We can use a stack to solve any problem iteratively, but solving it through recursion is often a nicer solution. Here's an example. I have a function called factorial that takes a parameter n of type integer and returns a value of type integer. The base case is when n is less than or equal to 0, in which we return 1. Otherwise, we return n times the factorial n minus 1. Here, we're breaking down the problem 1 less than was actually called. So, does the following code take advantage of tail recursion? No. The return value can only include the function. So, what tail recursion is basically if the recursion call is the last thing done in the function before returning. In this case, we see that when the recursion function is called, it has to be multiplied. The return value of factorial has to be multiplied with the n. So it's not the only thing that's being done in the return function. So this is not a tail recursion function. So question 1. We write a tail recursion function that computes the factorial of a number. What is its complexity? So the complexity is O of n, because you would have to go over every single number from n by doing -1. But I'll give you guys, pause the video for 2 minutes and come up with the tail recursion function for factorial. So here's the answer. So as seen on the previous slide, this is a tail recursion function where we define a partial factorial because we want to get the factorial of n, and we send in a partial every time we call the recursion function. In this case, the base case is 1 because it could be less than or equal to 0, but even if it hits 1, you're returning the partial factor, and 1 factorial is equal to 1. 0 factorial is also equal to 1, so it doesn't matter what the base case is. And we know we're not going to hit 0 because we're always subtracting the number by 1. So, and the other thing that we're doing is, for optimization purposes, is basically multiplying. For every recursion call that we're doing, we're having a partial factorial. So let's take an example of 3. When we call the function with an initial value of 3, it would skip the base case because n is not equal to 1. Then we go into the return case where we call factorial with 2, 3 times partial factorial. And here the partial factorial would be 1 because you would not want to multiply any number with 0 because that would only lead to 0. So if you call the factorial function with 3 and 1, you would have 3 as your call to the factorial again with 2, 3, and then you would call you would not hit the base case, then you would have 1, 6, and then you would hit the base case and you return 6 as your final answer because that's the last thing the function does. So this is an example of a tail recursion function. And 3 factorial is also 6, so it gives you the correct answer with no overhead. Here's question 2, a bit on the harder side. So write a function to reverse a string using tail recursion. On an initial call, the start is 0 and the end is string length of the string -1. So take about 2 to 3 minutes, pause the video, and come back later. So here's the answer. So we have a function called reverse string, which is a void, so it doesn't return anything but modifies the string in place. We take the string itself that we're going to be reversing. We're going to take the start index and the end index. And the base case is going to be when start is greater than or equal to the end index. And if it is greater than or equal to, we just return because it's a void function. In this case, we do the following thing. We create a new variable called temporary or temp, and we keep the character at index start in temp. Then we reassign the character at start with the end character, and then we assign temp to the end character. So we're basically flipping the characters by using the temp variable here. So every time it goes to the next recursion call, we increase the start index, so it goes +1, and the end index goes 1 minus that. So every time we go to the next recursion call, the start and the index keep getting closer and closer, and as soon as they equal each other or start becomes greater in the odd cases, it would return the string itself. So what is the complexity of this function? The complexity of this function would be O of n, because if the character has a size of n, we would be doing O of n by 2 because we're only going up to the middle point. And when start is equal to n, we would be at the middle point, so n divided by 2. But then if we just round it up, we have a linear case, so it's O of n. The next chapter is on object-oriented programming, OOP. In this one, I'm just going to be doing a bunch of explanations. There are not a lot of examples. Any examples that may come through object-oriented programming is more likely to be on the multiple choice questions. Okay, so what is object-oriented programming? Object-oriented programming is a fundamental programming concept used for software development and relies more on the object and data structure and its interaction with each other. Some advantages here are modularity. For modularity, we try to create independent modules that can work together. The second one is reusability. For reusability, we use independent modules in different ways based on the given problem. The third one would be efficiency. The fourth one would be maintainability. For maintainability, it should be easy to understand, well documented, and can be extended if needed. So there are a lot more advantages here, but these are the 4 that I listed here. For efficiency, it's the same as what it means. Efficiency, make the code more efficient so that there's no overhead or there's not too much overhead. Because using a lot of resources can also imply there's more cost, and that is what you're trying to reduce here. And everything is interconnected to each other. So what is an API? An API is an application programming interface. It is a set of definitions and protocols for building and integrating application software. Some examples are Google Maps, OpenAI, ArcGIS, and many more. And some of you might have also used APIs for hackathons or any of your personal projects. Some of the advantages of APIs are it increases interoperability. It means that you don't have to worry about the underlying structure of how the function or an API is implemented. You would just have to call it and know what input parameters it takes and the return value that it does. It is really efficient and it can improve flexibility. So you can take a bunch of APIs from different sources and combine them into your own project and make them work with each other to give you more of a desired result for the given situation. In C, it consists of a function declaration, constant, structures, and documentations required for the user or programmer who is using the API. Now, coming back to OOP, there are a couple of more concepts. The first concept that I'm going to cover is encapsulation. For encapsulation, it is the details of implementations are encapsulated or hidden from the user to promote security. Information hiding increases software reuse as modules become more independent of each other and are loosely coupled, meaning they're not tightly woven with each other, meaning if you change one of the functions, it breaks the other function. That is what we're trying to avoid in this case. That's what it means by loosely coupled. For access modifiers, there are 4 types of access modifiers: private, public, protected, and package private. The first 2 are the ones that I'm going to be covering. For private, you can think of private as a local variable, that it only belongs to the scope. So if I define a class called animal and a variable inside it or a field inside it to be private, I can only call that variable within that same class. So if another class extends the original class animal, I would not be able to use that private variable. The second one is going to be public. You can think of public as global variables. You can access it from any of the classes or any of the instances, and it's always accessible. You would not get any errors. For protected, it kind of is in between both private and public. So yeah, I think for A48, you're only covering private and public. And in further classes like BO7 or CO1, you'll be covering about protected, package private, and you'll be actually using object-oriented programming languages such as Java, C++, and more. The next concept that I'm going to be covering is overloading. Overloading. It means defining functions that have the same name but different function parameters. Meaning I can have 2 functions called sum, but one sum function can be taking 3 parameters, and the other function could be taking 2 parameters. And they do the same thing by adding all the input parameters. Like a function sum could take a, b, and c of all type integers. and the return value could just be a plus b plus c. In the other sum function, I can only take two input variables, a and b, and the return value would be a plus b. The next concept I'm going to be taking care of is overriding. Overriding is defining functions in subclasses using the same function parameters and return type. Meaning if I define a function called money that has amount as a variable, and I extend that to be Canadian dollars, I can override the amount or the amount type to be in Canadian dollars. And it would be using the same parameters and the same return type. So you're not changing any of those details. So you can use it for a more specific purpose in the Canadian dollar subclass. And these two things are different. Make sure to keep that in mind. The next one is polymorphism. In polymorphism, every object of a subclass is also an instance of a superclass, but not vice versa. So an object of subclass can be used wherever its superclass object is used. For example, let's say we define a class called shape, and we have a subclass that extends shape called a rectangle. In rectangle class, let's say in the main function, I am creating an object of a shape, and I do some operations with that object. So what this polymorphism is basically saying is I will be able to replace shape with rectangle, and it should still behave the same way, assuming that the functions are related to like parameter, area, or something like that. So every object of a subclass is also an instance of its superclass, but not vice versa. And the last one is going to be about inheritance. For inheritance, we're define it as using hierarchy of classes representing objects that are related to each other and share common properties and behaviors. So just like the previous example, we have shape to be our parent class and rectangle to be the child class of shape. So any properties or functions defined in shape, like let's say area, perimeter, and other functions like that, like get shape or something like that. If we extend that class in rectangle, meaning rectangle extends shape, we are able to use all those functions defined in shape. So it inherits the properties of shape. And if I define, say, another class called square or circle, and I extend shape, square or circle are both able to use the methods defined in shape, like area and perimeter. So that's it for the A48 review seminar. Thank you for coming, and good luck.